Good morning. So today I want to go through the solutions to the probability test that I gave you last week. I haven't actually corrected all of them at the time that I'm recording this, so later I'll give feedback on how you've done, but I wanted to give the solutions to you so you can go through them and clear up anything that you didn't understand in the paper. Okay, question 1. A bank issues a unique 6-digit password to each of its online customers, and the password can contain any of the digits 0 to 9 in any position, and the numbers may be repeated. Okay, so for example, we could have had 0000000. Wouldn't be a very good password, but we could. So you can repeat the 7s and so forth. Now we remember from our pigeonholes, and it's going to have 6 digits, so let's do 6 boxes. Usually we go 9876 because once we've used a digit, we can't use it again. But in this case, 0 to 9, there's 10 options. 10 options, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So I have 10 choices for my first digit, but I can reuse that. So I still have 10 choices for my second, third, fourth, and fifth, meaning that I have, when I multiply those together, I have 10 to the power of 6, or 1 million different possible combinations for a valid password. How many passwords do not contain any 0 then? So again, with my pigeonholes, my 6 boxes, 1, 2, 3, 4, 5, 6, and now I only have 9 choices for each box, but again, I can repeat. So I maintain 9 choices for each box rather than reducing at each step. So when I put that into my calculator, 9 by 9 by 9, 6 times is 9 to the power of 6, which is 531,441. 531,441. So it's nearly halved just by taking out one of the digits. One password is selected at random from all the possible passwords. What is the probability that it contains at least 1 0? So something we've got to think about here. The probability of at least 1 0 means it's every other one of than these. So that means it's the same as the probability of no zeros. Bit of a confusing question. So this is 1 minus the probability of no zeros, which is 1 minus 531,411 over 1 million. And that gives you, and did they say how they want us to write it? No, so we'll just write it as a decimal. And that's going to be 1 minus 531,441 over 1 million. Okay, so we type it in like that, and we get 0.468559. And let's go to 2 decimal places, so that's approximately 0.47. A 47% chance that it has at least 1 0. Now, John is issued with one password from the bank that's like this, and each time he wants to access his account, the bank website requires him to input 3 of the digits in the box provided. So he might be asked for the second, fourth, and fifth like this. In how many different ways can the bank select the 3 required boxes? Okay, bit of a difficult question here. So we have 6 options, and we're choosing 3 of them. So that's our 3 boxes. These are the 3 that we're picking, the 3 digits that the bank is going to ask for. It could ask for the first, second, third, fourth, fifth, or 6th digit here. So there are 6 options there. But once we've chosen the first one, we now just have 5 of the other digits to choose from. So there are 5 possibilities for the second one, and now we've chosen 2, leaving us with 4 possibilities for the third one. And when we multiply those together, we have 30 by 4, that's 120. 120 ways of selecting those digits. So 6, I'm just going to double check it, 6 by 5 by 4 gives me 120. Okay, now I would consider that that was a bit of a tricky question. It was stuff we'd done before, but there was sort of little tricks in each part of it as well. Let's look at question 1. An experiment consists of throwing 2 standard fair dices and recording the sum of the 2 numbers, adding them together. So sum means add. And we must complete the table. So they're all in diagonals like this. So we complete the table like that. Find the probability of getting a total of 7 or a total of 11. So we have 1, 2, 3, 4, 5, 6 sevens, and we have 2 11s like that. So the probability of 7 or 11 is the probability of 7 plus the probability of 11, because they are mutually exclusive. You either get 7 or 11, you can't get both. And that's going to be 1, 2, 3, 4, 5, 6, 6 out of 36, plus 2 out of 36, which is 8 out of 36, and that simplifies to 2/9. Find the probability of getting a total which is a prime number. So we need to know our prime numbers. 2, 3 is prime, 5 is prime, 7 is prime, and 11 is prime. So a prime number, just to remind us, has exactly 2 factors: itself and 1. Just a reminder there, even though it didn't come up in this case, 1 is not a prime number, because people tend to think that it is, and it's not. So how many do I have here? So the probability of getting a prime will be the number of primes out of 36. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 out of 36. That's quite high, nearly half of them are prime. Okay, part B then. A car distributor sells Ford cars and Renault cars. It has 30 cars for sale on a particular day. 18 are Renault, or 18 are Ford, and 12 are Renault, adding up to 30. So my total, they're going to ask me probabilities now, is 30. 7 of the Ford cars are red, and 4 of the Renault cars are red. One of the 30 cars is chosen at random. What is the probability that a car chosen is a Ford car or a car which is not red? Now, we have to be careful here. These aren't mutually exclusive events, okay? It's probably useful to do a Venn diagram for this. It's not the only way of doing it, but I would probably do something like this. Ford and red. Okay, so of the Ford cars, 7 of them are red. And of the Renault cars, 4 of them are red, meaning that I have a total of 11 red cars, and the remaining Ford cars, 18 minus 7 equal to 11. The remaining 11 here are Ford cars that are not red. Out here, I have the Renault cars that are not red. I have 8. Okay, so my total here is adding up to 30, but my total of Ford and red, and this guy is 18, and this guy is 11. forward or red is going to be 11 plus 7 plus 4. Let me write that in English as well. Forward or red. Union and or are the same thing in set notation. So that is 22. So the Venn diagram helped me work that out, but that's not the only way of doing it. That's forward or red, which was not what I was asked for actually. I was asked for forward or not red. Okay, so either forward or not red. Or not red. Now, we can be forward and red, or we can be these guys that are out here. So that's what we're talking about here. In set notation, this would be F union R complement. So we'd write it in set notation. So what we're talking about is everything. So we're including the red Ford cars, but we're not including the red Renault cars. The difficult thing about this question was interpreting what they're asking. So forward or not red means forward or the Renault cars that aren't red. Okay, so everything apart from the 4 red Renault cars. And doing the probability, calculating the probability then, that's going to be everything but those 4, 11 plus 7 plus 8 out of 30. And that's going to be 26 out of 30, which simplifies to 13 out of 15. So just the main thing here that might have caught people out is that we do include the red Fords. Now, you may have done that differently, and that's fine. I find the Venn diagram helps me visualize it, but if you did it another way, that's okay as well. And you might have just read that and gone, oh yeah, it's everything apart from these 4. And then you would have done 30 minus 4 to get 26. 26 out of 30 gives you your probability there, your 13 out of 15. Okay, I hope that's clear. If you're still finding that a bit confusing, just let me know and I can go over it again. Or let me know any questions where you got stuck if there's something that you're still not understanding. Thank you. Right, the third question then. We have a biased die used in a game. So if we had a non-biased die, we'd expect all of the probabilities. So for a non-biased die, it's always useful to have this. Each probability would be equal to a 1/6. And because they've given them in decimals, I just want to make a quick note for myself of what the decimal value of a 1/6 is, and it's 0.16666, so 0.17 around. It's around a 17% chance of each number coming up when it's not biased. Those are the numbers and their probabilities. So we might call these x and p of x. And that's our probability distribution table. What is the expected value of the random variable x, where x is the number thrown? So remember, the expected value of something is the sum of the x values multiplied by their probabilities. You don't need to write down the formula. So it's 1 by 0.25 plus 2 by 0.25 plus 3 by 0.15 plus 4 by 0.15 plus 5 by 0.1 plus 6 by 0.1. And you put those into your calculator in one go. Once you've written it down, it's fine to just type it into the calculator. So 1 by 0.25 plus 2 by 0.25 plus 3 by 0.15 plus 4 by 0.15 plus 5 by 0.1. Do write it down. I know it's a bit tedious both writing it down and typing it into your calculator, but if you make a mistake putting it into your calculator, the fact that you've written down the correct calculation means you'll get most of the marks. 29 over 10 or 2.9. We did a calculation in class and we found that the expected value of a non-biased die is 3.5, so this is significantly lower. Now we're going to use it. There's a game at a fun fair and it costs €3 to play the game. The player rolls a die once and wins back the number of euro shown on the die. The sentence below describes the difference between using the above biased die and using a fair unbiased die when playing this game. So if you play the game many times with a fair die, you will win on average what? She just talked about that we know that the expected value of a fair die, 1, 2, 3, 4, 5, 6, is 3.5 because it is a sixth in each case. I wouldn't use the decimal value here. I would use so the expected value of my fair die is going to be 1 by a sixth plus 2 by a sixth plus 3 by a sixth and so on, plus 5 by a sixth plus 6 by a sixth. And I happen to know this one. It works out to be 3.5. So that's the average value. So if you play with a fair die, you will win an average of €3.50 per game, which means you win 50 cent per game. If you play with a biased die, you will lose. So you'll win an average of 2.9, but you lose 10 cent. So with the unbiased, you pay €3 and you win 3.50. So therefore, you're making 50 cent each game. And with the biased die, you pay €3 and you win back €2.90. So you're losing 10 cent on average each game. You might win, depending on how many times you play, but that's the whole thing with gambling. Okay, so that was an expected value question. And that was the 3 questions that you had. So I just want you to take your time, go over those, make sure you understand them. I'll have your corrections back to you as soon as I can. I may even have them back by the time you're looking at this video. I make them ahead of time. So do please let me know if you have any questions. You might comment on today, Monday's Google Classroom, if there's something that you want to ask so that everybody can get the benefit of the question and the answer. Thank you.